Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, we are the Pharma, and now we want to elaborate the results from our scientific paper.
The printing equipment examined in this investigation performs according to various concepts, which leads to a diverse consumption of electricity. Every scenario requires linear movement to produce the printed item. Nevertheless, FDM, DPE, and DIW creation specifically involve heating to activate the nozzles and, in particular circumstances, the construction plate. On the flip side, SLS and SLA printing depend on the use of laser. Furthermore, two of these printing processes require supplementary hardware. The FDM printing process utilizes a hot melt extractor to prepare the polymeric fibers for printing, whereas SLA printing requires an oven for post-curing. As a result, we consider the power consumption of these additional hardware components to power both operating systems. Similar to other devices, three-dimensional printers consume resources while in passive mode. All 6 printers recorded a total power consumption of between 0.03 and 0.17 kW during a single hour. Among them, the IW applied the largest percentage of energy. The FDM printer's number reflects some funding from HME. We observed a significant disparity between the two, with the tiny FDM printer requiring 62.5% less electrical power than the massive FDM printer. The DPE printer, a sophisticated variant of FDM that automatically expands material, had a power bill that was identical to both the tiny FDM printer and its backup usage from the HME. Nevertheless, it required a smaller amount of electricity compared with the huge FDM printer paired alongside the HME. Although the SLS printer has the greatest quantity, it utilizes roughly the same amount of resources as the standard DIW and large FDM printers. The heating oven commonly used in SLA printing led a baked-out solution, resulting in minimal output. The measured carbon dioxide output varied from 5.98 to 33.99 grams of equivalent carbon dioxide per hour. This amount allowed for long-term calculations of greenhouse gas emissions.
If the machines remain inactive for a single day, a month, and a year, the carbon footprint might vary from 143.52 to 813.36 grams CO2, 1,305.6 to 24,400.8 grams CO2, and 51,667.2 to 292,809.6 grams CO2 respectively. Letting machines be on reserve for a long period of time is manifestly hazardous limit. Therefore, ensuring that machines are off when not in use should be the most beneficial course of action. We determine the amount of energy needed to produce 10 printlets for each of the 6 printers. These calculations encompass the power requirement throughout the beginning phase of preparation, such as heating up and calibration, the precise printing procedure, and any subsequent cooling devices. As previously mentioned, the calculation took into account the energy required for any additional equipment. For all printers, except SLS, the annual energy usage figures range from 0.06 to 0.58 kilowatt hour. Just like in sleep mode, there was a clear distinction among the two FDM printers. The smaller printer consumed 60.8% to 53.4% fewer kilowatt hour over the larger machine, according to the HME frequency, high 175 degrees Celsius and low 75 degrees Celsius. While the printing settings and ultimate production duration are comparable, there is a significant difference in size. The SLA printer consumed 0.14 kWh of energy for its operation. Additionally, post-print curing might necessitate the application of heat. Previous research has demonstrated that we can post-cure SLA printed drug delivery devices at 60 degrees Celsius for 20 minutes. Post-print curing resulted in a 0.20 kWh increase in electrical power use. However, even with this increase, SLA remains one of the least fuel-consuming techniques.